Welcome to a screencast on energy basics that relate to chemistry. All chemical and physical processes involve not only matter changes, but also energy changes. For example, in an oxyacetylene torch, the fuel acetylene, or C2H2, reacts with oxygen, it burns, it combusts, it makes carbon dioxide and water, and it produces a lot of energy. In fact, it produces enough energy to weld railroad rails together. This kind of a process, a reaction that gives off energy, is called an exothermic process. Now, of course, on the other hand, we have things like chemical cold packs, which contain ammonium nitrate, NH4NO3, and water. And when these are set off, we have a chemical reaction or dissolving process that occurs, and heat is absorbed, and the cold pack actually gets colder when it absorbs heat, and this is what's known as an endothermic process. Now, let's look a little bit at energy and heat and work and some of these things that pertain to chemistry and chemical reactions. And first, let's note that energy is the capacity or ability to either supply heat or to do work. And energy can be classified as either kinetic energy, which is the energy of motion, or potential energy, which is stored energy that's potentially available for use. So a car, or for that matter, a moving molecule, has kinetic energy, its energy of motion. And then chemical bonds and cheeseburger have stored energy or potential energy that can be available for use. Now, in general, we know that energy can't be created or destroyed, but we can convert energy from one form to another. This is one way of stating the law of conservation of energy, or the first law of thermodynamics. And there's lots and lots of examples of this. In fact, pretty much everything follows this. And for example, if somebody climbs up a ladder to the top of a diving board, they're converting some energy that's stored in their muscles, which they originally got from food that they ate, which originally came from the sun, etc. And they're converting that energy into some stored energy, some potential energy due to their height above the surface of the water or above the ground. And then when you jump off the diving board, that potential energy is converted into kinetic energy or energy of motion as you fall or leap off of the diving board and head for the water. Now, chemists often are going to be following heat, and heat is the transfer of what's called thermal energy between two objects that are at different temperatures. For example, you have a hot cup of coffee, high temperature cup of coffee, and heat is some thermal energy that is transferred from the hotter, higher temperature cup of coffee into to your body if you drink it. Now, thermal energy is actually just the kinetic energy of molecular motion. So at a molecular level, molecules move around, they have kinetic energy, and if the molecules are at a low temperature, in other words, if we would say that the object containing the molecules is cold, then its atoms are moving slowly. And here we have a representation of some atoms or molecules that are not moving very quickly. And if we have a high temperature object, and we would say it's hot, well, then its atoms are moving more quickly. And so here's a representation of a high temperature object, and its atoms or molecules are moving faster. Now, we know that heat always flows from a higher temperature or hot object to a lower temperature or cold object. Heat flow is always in the direction from higher temperature to lower temperature. And the heat flow, if given a chance, will continue until we reach thermal equilibrium, where the two objects that are in contact with each other are at the same temperature. Now, of course, these are very simplified situations. In most of the world, most situations, things are a little bit more complicated than this in terms of interpretation, but these basic principles always apply. Now, chemical energy is energy that is stored in the bonds of chemical substances. And, for example, in coffee, there's caffeine, and a caffeine molecule, which looks like this as a ball and stick representation, has a bunch of carbon, hydrogen, oxygen, and nitrogen atoms bonded together as shown, and there's energy stored in these chemical bonds. You're probably more familiar with stored energy and chemical bonds due in the foods that you eat, in fats and in carbohydrates, and as well as, of course, in proteins. But all chemical substances have energy stored in their bonds. And we often represent this in an energy diagram, where the red line here represents the energy of our reactants or our starting materials for a particular chemical reaction. And the second red line here represents the energy of the products. And the y-axis represents energy from low to high, kind of typical thing. And what we normally do is our x-axis, we call a reaction coordinate progress of reaction, as we go from reactants on the left to products on the right. And this particular reaction, or energy diagram for a reaction, represents a case where energy is given off in a chemical reaction. The products have less energy than the reactants. They're lower in energy on the diagram. And since the products have less energy than the reactants, then they are more stable than the reactants. And of course, the other kind of reaction, we can have products that have a higher energy than the reactants. And when energy is absorbed in a chemical reaction, the products have higher energy or more energy than the reactants, and therefore the products are less stable than the reactants. Now, chemists use something called enthalpy, which we symbolize by H, to follow energy changes during chemical reactions. Every reaction has what's known as a delta H, enthalpy change, associated with it. Enthalpies are as important to the chemical reaction as are the reactants and products, and they're treated quantitatively the same way because they're proportional to the amounts of substances involved in the reaction. And probably worth noting that enthalpy is technically heat flow at constant pressure, but we are usually going to perform reactions at constant pressure under those kind of conditions. And so most of the time, certainly at a general chemistry level, we can just think of enthalpy of reaction as just the heat or the energy involved in the reaction. If you go on to study at a higher level, then the technical difference or situation becomes a little bit more important and precise. And that is it for an introduction to some energy basics that pertain to general chemistry.